Hi, everybody. Good morning or good afternoon, depending on when you're seeing this. I'm sorry I can't be with you today, but hopefully this review helps you a little bit. Um, and I really hope you're being awesome for Mrs. Frankenhauser. I'm going to ask her how you were, and you will gain or lose brownie points accordingly, so please let me give you tons of brownie points on Friday. All right, so I am going to do a test one review. I'm going to go over all the stuff I put on your study guide. And what I want you to do right now is take out a sheet of paper. So I'm going to give you a second to take out a sheet of paper. So I want you to take some notes while I'm doing this. So if there's anything that I go over that you don't remember or you don't have in your notes, this is your opportunity right now to write it down and study it tonight for the test tomorrow. Paper time. All right, so the first thing we talked about with science is we talked about a definition of science. And if you remember, this was on quiz 1. A lot of you got it wrong, and this is honestly, it's a simple memorization. There's nothing very complicated about this. This is just a definition that I gave you. So there's 3 things that we talked about what science is. So the first thing we said science is, and you guys are all familiar with this, is it's a body of knowledge. So there's a collection of facts that make up science. All right, the second thing that we said science is, it's a process. So we can figure out things in our everyday lives through science. And finally, the last thing we said science is it's a way of knowing. So you can know that you love your parents, but that's not through science. But you can also know some things through science. For example, I know that if I drop this piece of chalk, it will fall, and I know that through science. So these are the 3 things that I'm looking for when I ask you what science is. So if you don't have these or you don't remember them, write them down now. All right. So the second thing that you guys asked me to review were myths of science. So I want you to recall, we went over a true-false test to see how much you knew about science at the very beginning of our year. And there's a few of them that are very important that I want to go over with you again. So, the first one that we talked about that should be very fresh in your mind is about theories and laws. So there was a myth, and there is a myth, that people believe that theories will one day become laws. But in truth, theories and laws are equal, and scientists need both of them, and they just tell us 2 different kinds of information. So, theories will never become laws. The second myth, or another myth that we talked about, was that there's a lot of male scientists out there. A lot of men are in science. So one myth that people believe is that male scientists are somehow better than female scientists, or men somehow think better scientifically than women do. And this is totally a myth. I'm a scientist. I am a woman, of course, and there are many female scientists who have made great discoveries. So, men are not naturally better at science than women. Both men and women have the capability to be good scientists. Another myth that we talked about that a lot of people believe is that science can one day solve all of our problems. And as a scientist and as your science teacher, I love science, but There is no way that science can solve all of our problems. So I want you to think about all the problems in the world that we have today. There are wars going on. There are people who are starving, and science cannot solve all of our political problems or religious problems. There are problems that are outside of the realm of science. But science can solve a lot of problems. It's just important to realize that science can't solve all of them. All right. These are the main myths that I want you to remember. I know we went over some other ones, but these ones are going to be very important for your test tomorrow. Hint, hint. So if you don't remember these, write them down. All right. Another thing that I got asked to go over was scientific habits of mind. So I want you to recall that a habit of mind is something that makes a scientist a good scientist. So think about a habit that you have that's maybe a healthy habit. If you work out, if you eat good foods, these are healthy habits. Just like we have healthy habits or bad habits, there's scientific habits, things that people do that make them good at science. So we talked about a lot of these. We talked about them when we talked about female and some minority scientists that were really important in recent history. And some of these I'm just going to remind you of. One of them is creativity. Now, there's a myth that science is not a creative endeavor, that people aren't creative when they do science. And this is actually totally false. The best scientists out there are very creative. So if you've heard of Leonardo da Vinci, he was a great inventor, a great scientist, but he was also very creative. So scientists have to be creative to come up with solutions for their problems and figure out how they're going to test something that they want to know. So creativity is definitely used in science, and that's another myth that I didn't mention before. But if you recall, that was a myth that we talked about, that science doesn't use creativity. It does, and good scientists are very creative. Another one that people don't often think of is honesty. Now, scientists need to be honest because when they're reporting their findings, they need to be as truthful as possible. Their findings could tell us something very important, especially when it comes to medical fields. They need to be very honest. If you think about somebody who's researching medicine or things that could potentially save lives, if they're not honest about how drugs work, they could harm a lot of people. So it's very important that scientists are very honest about their work and that they've actually done their work and done their research. So good scientists do not lie about their findings, and they actually do their science work. Another science habit of mind we talked about was determination, being determined. So a lot of the female and minority scientists we talked about were up against huge odds. They were not allowed to pursue education like normal white men were at the time, and there was a lot of animosity or hatred towards them for doing what they did, but they were very determined. So good scientists are always determined to find an answer, to keep going. They persevere. Another one that we talked about was good scientists have a thirst for knowledge. So they want to know about the world around them. And everybody's born curious. All kids are curious. You've heard little kids ask why over and over again. Good scientists, they also ask why. So they're always wanting to know what's going on, why is this happening. They want to figure out the world around them. So these are just 4 scientific habits of mind that I want you to remember. There's other ones that we talked about. You can review those in your notes, but here's some main ones. All right. So, speaking of science, we need to know what kind of questions science can answer. Science can't answer all questions, and it can't solve everything. We've already talked about that. So, kinds of questions that science can answer. So, science can only answer questions that can be disproven. If I tell you that my favorite kind of ice cream is vanilla, or if I ask you if you think vanilla ice cream is yummy, you can't disprove that. That's not a science question, that's a matter of opinion and belief. If I asked you what is art, that's not a science question either, because that's a matter of opinion. What one person considers art, another person might not. So science questions can be disproven. If I ask you, will a plant grow taller if we give it fertilizer? That's something that we could investigate and disprove or potentially find evidence for. So that's a good science question. Good science questions can be disproven. And if you recall, some of you might be confused of why I'm saying disproven and not proven. In science, we don't prove anything. And I know that's a really weird way to think about things, because you might be saying to yourself, but Ms. DeBari, how have we not proven that gravity works? Everything in science is tentative, so it could possibly change. While certain things like the law of gravity is not likely going to change, it could. So we have to accept the fact that science could one day change. So we don't ever prove anything in science. We can disprove it, or we can find evidence for it. All right. Speaking of proving and disproving things, one thing I want to talk about is when we do lab reports. So when we're doing an experiment and we write up a lab report, there's certain things that need to go in your lab report. So we're going to talk about those. The first thing that goes in your lab report is a problem. And this is a question of what are you trying to solve? Next is your hypothesis. And your hypothesis is not just a guess. It's a very well-educated and well-supported prediction. So it's reasonable and it's logical. And scientists who make a hypothesis are not just making a random guess. They have a lot of evidence for what they think is going to happen. So next in your lab report is your materials and procedure. So remember, whenever you write out your materials, you write everything you used and be as specific as possible. So if you used 200 milliliters of water, don't just say water, say 200 milliliters of water. Be as specific as possible. And then our procedure, when we write it out, we write step by step. So if somebody reads it, they should know exactly what you did. Next, when you actually do the experiment, you should get some kind of data. So when we're writing up a lab report, we want to tell people, what'd you get? Next, we have the analysis, which I've told you guys over and over again is the real meat of our lab report. This is where we can tell somebody what happened, what patterns we see, what might have gone wrong, what we predict would happen if we changed the experiment, how we could improve. There's a lot of things that we answer in this section. And finally, at the end of our lab report, we have the conclusion. And if you recall, we don't prove anything true in science. So we never say that we proved our hypothesis correct. We say that we found evidence for it. So in your conclusion, you're going to go back and look at your hypothesis and reflect on what you did and say either you found evidence for your hypothesis or you didn't, and explain why or why not and what happened. since we're talking about doing lab reports, most of you recall we did some work with mean, median, and mode because those are ways that scientists analyze their data. So sometimes you're going to get numbers, and you might want to find out the mean. We wanted to find out the mean of a set of numbers. First, we would add up all the numbers, and then we would divide by how many numbers there are. So, if we had a set of data like this, we would add up 2 plus 3 plus 4 plus 2 plus 1. And we would divide by 1, 2, 3, 4, 5. And that's how we find the mean, which is also the same thing as the average. Now, another thing that scientists might need to use is the median. The median is the middle number in our set of data. So say we have another set of data, 0, 2, 4, 4, and 5. So the median is going to be the one in the middle. So in this case, 4 is our median. Now, what would happen if we had an even number of data points? So we have 0, 4, 4, 5, 6, and 7. In this case, we have 2 in the middle. We're not going to say both 4 and 5. We're going to take the mean of 4 and 5. So 4 plus 5 divided by 2 equals 4.5. That's our median, or the middle number. And the last thing is the mode, which is probably the easiest thing to calculate. The mode is the most common number we get. So again, if we had a set of data like this, the most common number here, it's 4. So our mode would be 4. Now what would happen if we had a set of data like this? 0, 3, 4, 5, and 7. In this case, there is no mode. They all appear equally. So you would tell me no mode. All right. All right. Since we're talking about numerical data, let's talk about the difference between quantitative and qualitative. So sometimes when we're doing science, we take what's called a quantitative observation. And if you look at this word, it sounds like quantity, because we're taking a piece of numerical data. We're going to record a number. So for example, if you were doing a study and you wanted to see how tall plants grew, you would be taking that data in centimeters probably, or meters. That is going to give you a number. So that's going to be a piece of quantitative data. Now, on the other hand, if you were dissolving a gobstopper in, say, Sprite, and you wanted to see what color it was going to turn, you would be recording colors, but that's not a number. You're looking at the qualities. So think about the qualities. These are going to be descriptions. So a qualitative observation might be red or fizzy. Anything that describes something that's not a number is qualitative. On the other hand, quantitative will give you numbers, like 4 centimeters, 10 gallons. Whatever your number is, if you have a number, it's quantitative. All right, another thing a lot of you asked me to go over was precision versus accuracy. This is still kind of foggy for some of you, so I'm going to talk about it a little bit more. First, I'm going to give you the definitions, and then I'm going to tell you how to think about it in a way that's very visual. So it's kind of the example we've already gone over in class, but I'll go over it again. So accuracy. Accuracy is how close we get to the actual value, the true value. So say for instance, I'm 5'8". If I'm measuring myself on a wall and I get that I am 5'6", that's not very accurate because it's not close to my true height. But if I use a meter stick or yardstick that tells me that I am 5'8", that's accurate. Precision is a little bit different. So in everyday language, you might use these interchangeably, but they're not interchangeable in science. They're two different things. So precision, on the other hand, is how close our measurements are to each other. So if we say we are going to weigh ourselves on a scale, and that scale tells us that we are 100 pounds. And then we get off the scale, we step on the scale again, it says 100 pounds again. We get off, we get on, it says 100 pounds. It's very precise because it's telling us the same measurement each time. However, if we're 120 pounds and it tells us that we're 100 pounds, it's very precise, but it's not very accurate. So in science, our numbers can be accurate, they can be precise, they can be both, or they can be neither. So I want you to imagine a case where you're using a scale and you're weighing yourself. And let's say that you weigh 120 pounds. So if you step on the scale and that scale tells you that you're 120 pounds, and you know for a fact that that's your true weight, then that scale is very accurate. Now, if you step off and you step back on and it tells you that you're 150, then it's not very precise because the scale is giving you a different reading each time. Now, if that scale continually tells you that you're 120 pounds, it's both accurate and precise. So if you recall in class, we talked about an example of accuracy and precision with a dartboard. All right, let's say that you're throwing darts, and this is the bullseye, and you want to hit the bullseye. So in this case, you're hitting around the bullseye each time, so you're pretty accurate, but you're not very precise because you're hitting all over the place. Now let's say you also want to hit the bullseye, but for some reason you always hit to the left of the bullseye. So in this case, you're not very accurate, but you're precise. You're always hitting in the same place, but this isn't good enough because scientists want to be both. So this is an example with all of the dots on the bullseye that's both accurate and precise. We're hitting where we want to hit, and we're doing it over and over and over again. Accuracy and precision are really important to scientists because when they're experimenting, they want to find data that is correct. And if they are doing something, let's say with medicine, or there's a practical application for their work, if they get the wrong numbers, something disastrous could happen. So let's think about NASA. If they are not accurate and precise in their calculations, they could send people way far away from the moon. All right. Next, we're going to talk about independent and dependent variables. So we talked about variables in class. And at the root word of variable is vary, which means changes. So a variable is something that could change in an experiment. So the first kind of variable we talked about was an independent variable. So the independent variable is going to be something that you change on purpose in your experiment. So in class we talked about an example. If we were going to see if fertilizer would affect how tall plants grow, what you are going to change is the fertilizer that you give the plants. So you're going to give some plants fertilizer and some plants no fertilizer. And that's your independent variable. The fertilizer, if you give them fertilizer or not, that's the independent variable because you personally are changing that. Now the dependent variable is just like what it sounds. It's dependent on this one. It is going to change because of this. So your dependent variable is going to change because of what you changed. So for example, if we put more fertilizer on plants, they might grow taller. So the height of plants is going to be the dependent variable. I'm personally not making the plants grow taller or shorter, but because I'm giving them fertilizer or not giving them fertilizer, they are growing taller or they're not growing taller. So this is the dependent variable. Finally, we talked about something called a control variable. Now, our control variables are things that we don't want to change in our experiment. So if we were testing how fertilizer affects plant growth, there's a lot of other things that could change, but we don't want them to change. So a control variable is a thing that you keep the same or constant throughout the experiment. So if we were experimenting with plants and fertilizer, we would want to make sure that our plants get the same amount of sunlight, are at the same temperature, in the same kind of soil, and they get the same amount of water. So we want to keep everything the same, other than our independent variable and our dependent variable. The reason for that is because scientists want to figure out a cause and effect relationship. So if you give a plant more fertilizer, will it grow taller? Now, if we change the light and the water and the fertilizer, we're not going to know which one of those three things led to a plant growing larger. So we want to identify a cause and effect relationship, and we can't do that unless we only isolate one thing at a time. All right. Next, we're going to talk a little bit about observation and inferences. So we did a lot of work on observations. I'm sure you guys all remember that I ate a raw potato and almond for you, and that was when we worked on our observations. So observations are things, is information we gather using our 5 senses. So a lot of people think that an observation is just something you see with your eyes. That's not necessarily true. We can observe the wind, and we may not see the wind directly, but you can feel it on your skin or you can hear it. So observations, remember, are all 5 senses, not just sight. Now, we also can make inferences, and an inference is a conclusion based on our observations. So, the day that I showed you what you guys thought was a candle and it was actually a potato, you saw it and you observed that it looked like a candle. So you made an inference that it was a candle. However, if you were able to use your other senses, you would have been able to realize that it wasn't a candle, it was a potato. So, inferences are conclusions based on our observations. So if we observe that somebody's getting pulled over on the highway, we might make an inference that they were speeding and that they're going to get a ticket. All right. One thing we went over in class was our metric prefixes. We talked about measurement. Now, there are non-standard units of measurement that we tested out, things like the pace and the fathom and the hand. These things are variable because everybody's hand's different. My hand is different from your hand. So, to avoid all of the differences, scientists came up with a very standardized system of measurement. And if you recall, it's called the SI system, or the international system. And to help you remember your prefixes, I came up with a way to associate your metric prefixes with animals. So I'm going to show you our staircase again. Okay, so in the middle of our staircase, we have our basic units. We've got grams, liters, and meters. So we measure our mass in grams, our volume in liters, and our distance in meters. But what happens if you want to go bigger or smaller than a gram, liter, or meter? That's where our prefixes come in. So let's say we want to go 10 times smaller than our gram, liter, meter. We've got deci. So I showed you guys deci dog. That's 10 times smaller. Now if you want to go 100 times smaller, we've got centi cat. And finally, if we want to go 1,000 times smaller, we've got milli mouse. So each time we go down the stairs, we go 10 times smaller or 10 times bigger. If you go down, you go 10 times smaller. If we go up, we get 10 times bigger. So if you want to know how much smaller milli mouse is than gram, liter, meter, you go 10 times, 100 times, 1,000 times. So milli mouse is 1,000 times smaller than gram, liter, meter. Now if we want to get bigger, we have a prefix called deca. This is decadolphin. Next we have hecto for hectohippo. And finally, we have kilophant at the very top. So if we want to know how much bigger kilophant is than milli mouse, we would count our stairs. So 10, 100, 1,000, 10,000, 100,000, a million. So Killiphant is a million times bigger than Millie Mouse. I recommend for you guys on your test tomorrow to be able to draw your staircase. I'm a very visual person, and I know a lot of you are visual people, and it might help you if you draw this out on your test. Alright, the very last thing I'm going to go over with you guys is theories versus laws. I know we talked about it yesterday, but I can't stress enough that a lot of people get this wrong. So, theories and laws. They are both of equal merit. One's not better than the other. They're both very important to scientists. The difference is what they tell us. So, a theory tells us why. A theory tries to explain why something happens in nature. So the theory of evolution tries to explain why organisms are changing over time. A law, on the other hand, just tells us what. The laws of motion just explain why things go or they stop. They don't really explain, or they explain what's going to happen, not why. So they explain that an object in motion will stay in motion. It says what's going to happen. It doesn't tell us why, though. So when you think theory, think why. When you think law, think what. All right, so those are all the topics that are going to be covered on the test tomorrow. Study your notes because most of your questions are going to come from the notes. If you'd like to review this video again, it's available online. You can view it as many times as you want. If you have questions tomorrow, you can email me. I'm very fast with email, so I'll try to email you back. Study hard, and I know you guys can all make a perfect score. So best of luck to you, and I will see you tomorrow. Have a great afternoon.